Okay, hello. For the last few videos we've studied mid-segments, perpendicular bisectors, and angle bisectors. And today we're going to look at medians and altitudes. And here's some information about medians and altitudes. What the heck is a median anyway? Well, we're coming close to exhausting all the ways we can find to connect sides and vertices together. Here's yet another way to connect stuff up. We go from the vertex to the midpoint of the opposite side. Why would you want to do that? Well, once again, it turns out that if we construct that line for each vertex in the triangle, they are concurrent. That is, they all intersect in one point, and that point is the centroid. Oh, pardon me, that's not the centroid. Hang on. Well, darn it, happens to me all the time. I thought I made a mistake and it turned out I didn't. Wish I could be wrong that way more often. Where the medians intersect is the centroid. Why would anybody care? Well, there is this little thing here, so if we drew another centroid, say, let's see if I can do it. Here now I have an intersection point. And if I draw the other median, it'll intersect right there too, assuming I drew them correctly. And the cool thing about the centroid is you can think of it as a balance point. Well, in this case, when we're doing it this way, you have to assume that the object you're balancing is, suppose this is actually, say, a wooden triangle, that it's uniform. In other words, if it's a 1/4 inch piece of plywood that you cut it out, everything is 1/4 inch plywood, so there's no difference in the weight. This part of the triangle would weigh exactly the same as this part and this part. And the center, this centroid, is also the center of mass. It's the point where you could put a needle right there, set this wooden triangle on top of it horizontally, and in theory it would just balance right there. It wouldn't fall off to any side. You use that when making mobiles. Those things that hang from the ceiling that are perfectly balanced. You use centroids for that a lot. And later on in science class, of course, you will learn much about center of mass. Center of math is somewhere else. I'm not sure where that would be. But the center of mass, that's the point where it would balance perfectly. That is the centroid. What about altitudes? Well, in the first place, what the heck is an altitude? It's kind of like what we called the height when in our 1/2 BH for the area of a triangle. It's the perpendicular distance, or it's the segment which runs from the vertex perpendicular to the opposite side. These run from the vertex to the mid-segment of the opposite side. We don't know where this is going to intersect the opposite side. It just has to be perpendicular. And there is only one line from this point to this line which is perpendicular. Why? Well, this is the distance from this point to this line. And there's only one right distance, and that is the perpendicular line to that point. Or, I guess I should say, the length of the line segment, which is perpendicular to this line and passes through this point. That's the altitude. And of course, every one of these has an altitude. Take this one and draw it here. Well, that's okay, but suppose we had a different triangle. do we do in a case like this? We're going to go from the vertex to the opposite side. We want a perpendicular line. Well, there are no perpendicular lines from this vertex to this opposite side. However, if we were to extend this, in other words, just continue this segment as a straight line, then we can draw a line from the vertex, which is perpendicular to the extension of this side. And then we did that, this would be the altitude. So if you can do it inside the triangle, fine. If not, you just extend one of the sides and drop the perpendicular down from the vertex that way. So we've got mid segments, we've got perpendicular bisectors, we've got angle bisectors. Now we've got medians and altitudes. The river of your mind must be fairly muddy by now. Nothing we can do about it. You know, the Greeks had a saying. It went mathos, pathos. Maybe I can just write it. It looked like that. They probably wrote it on the walls at school. Pathos means suffering. Mathos is learning. What it means is learning is suffering. There's no way to learn without doing some work. And if you didn't believe that before, you probably do now. I have to admit, this is not easy. Mostly because, well, it's all kind of new, and it's a different way of looking at things, and what you're doing is just analyzing the heck out of triangles, which up until now probably didn't seem all that interesting to you. Maybe they still don't. But it's a huge part of geometry, and that's why we're doing this. And there's a lot more interesting stuff coming up, but we're going to use all this for the more interesting things. And you can't always do the interesting stuff right off the bat. Sometimes you have to do the boring stuff and learn it so that you can put it all together into something more interesting. I think a good example of things that are actually kind of exciting that start out very boring. If you ever learned to snow ski, your first day skiing, well, a lot of people actually just quit. They don't even want to ski after having skied their first day because it was so boring and so little fun. You see, when you learn to ski, the first thing you have to do is learn to put your skis like this. That's downhill. That's called a snowplow. And you go down the hill at about 2 miles an hour. If you want to turn this way, you put your weight on that ski. You want to turn that way, you put your weight on that ski. And if you lean forward and put more weight in the front of both skis, you eventually come to a stop. Or at least slow down and then stop. As I say, this is super boring. You go down the hill at only a few miles an hour, and if that's all there was to skiing, no one would ever do it. But after you got this down, you spend a little time doing this, pretty soon you put your skis together and then you fly down the hill in control. You can put your skis together and fly down the hill your first day if you want to. In fact, I did that. I put the skis on, I rode the lift to the top of the hill. A guy I knew came up next to me and said, "Race it to the hill, bottom of the hill." I didn't think about it, I just took off and raced it. It wasn't until I got to the bottom of the hill it occurred to me, I don't know how to slow down and I don't know how to stop. So of course I cracked up pretty good at the bottom of the hill. So my first day of skiing wasn't boring at all, but if you're a normal person, it would be boring. And you shouldn't go flying down the hill until you've learned to slow down, and especially stop. And that's what we're doing here. We're doing all this boring snowplow stuff. If there was a way to just jump on the skis and fly down the hill in mathematics, some people would probably do it. I might, but I can't think of a way to do that, so we're kind of stuck with the slow way of learning. Oh, and if you're curious, I did win the race. There's an advantage to not knowing how to slow down. Well, let's do some problems now. Now in that first theorem, I just kind of glossed over it. But they pointed out that, I put this part up again to remind us that one thing the centroid does is produce lines that are 1/3 and 2/3. What the heck does that mean? What I'm saying here is that this whole line, BF, BP is 2/3 of BF. PC is 2/3 of DC. And AP is 2/3 of AE. Or you could go the other way. In other words, I could have said that FP is 1/3 of FB. DP is 1/3 of DC. And like that. You can look at it either way. But you need to remember that in order to work this problem, I think. Let's double check here. M is the centroid. CM, well, that's this here. That would be the long side of CR, and CR is a median. TS is 56. Okay. So let's figure out what we have here. CM, what we're trying to find is AM, which is this one here. If we knew what AQ was, we'd be done. Well, we don't have that. I went ahead and drew in what we know. We got CM is 36, that's this one here. MQ, that's this here, that's 30. MT, or, well, pardon me, this whole thing here, is 56. I have a feeling that a lot of these numbers are just red herrings, just there to confuse us. All they asked for is AM. Would be on this median here. AQ is the whole median. Well, remember, we know from down here that AM is 2/3 of AQ. Or conversely, MQ is 1/3 of AQ. Well, that should work if 30 is 1/3 of AQ. AQ is 90. However, they didn't ask us for AQ. They asked us for the long side here, which is 2/3 of AQ. And 2/3 of 90, well, that's 60. So that's right over here. These two numbers we didn't need. We wanted this, and we know that this is 2/3 of this. And they gave us what 1/3 of it is. So actually, a lot of you probably just instantly said, well, this must be 60. Because if this is 1/3, 2/3 is just double that. I laid out the algebra just to make sure that there was no confusion. It definitely is 60 from here to here. Well, another one of those someone made a mistake problems. What we have here is all the altitudes drawn in. And he is using the fact that the concurrency of the medians, the concurrency of the medians, that point where they all intersect, divides the medians up into 2/3 and 1/3. Well, that's fine, but you're kind of mixing things up if you do that, because he drew in altitudes, but he's using a property of medians. You can't mix them up like that. If you're going to draw in altitudes, then you have to use properties of altitudes. if you're going to use a property of a median, then you have to draw in a median. This perpendicular, this little right angle symbol, it helps tell you that this is an altitude. Remember, the altitude goes from the vertex to the other side on a perpendicular line, whereas the median goes from the vertex to the midpoint of the other side. So he just confused the two. He used a property of medians and applied that to altitudes. You can't do that. Well, our job is to find the measure of angle A, BC. That's this big one here. And what information do we have? Well, DB is perpendicular to AC. Let's just draw that in so we don't forget. It's our right angle symbol. Find DC and the angle of ABD. Okay. Well, what we have here is an isosceles triangle. So it may not matter, but we do know right off the bat that these two angles are congruent. We also know, let's see here, this is a perpendicular bisector for an isosceles triangle, which means it is also an angle bisector. We had a theorem back on in angle bisectors that we showed that the angle bisector and perpendicular bisector of the opposite side of the angle are the same for an isosceles triangle. So this is both angle bisector and perpendicular bisector. Well, angle bisector means these two angles are congruent, so we can draw that one in as 22 degrees, and the measure of this total must be the two together, so that's 44 degrees. What about DC, the length of DC? Well, again, since we know that our angle bisector for an isosceles triangle is also a perpendicular bisector, CD and DA are congruent, so the length of CD must be 6. So this is 44, and this up here was 6. We just had to apply what we knew about angle bisectors. And of course, isosceles triangles. If this wasn't an isosceles triangle, we'd be in trouble. Well, here's another one where we just have to use geometry to figure out how to set up an algebraic equation. And this time they didn't write the values in for us. We have to do it. So we got BD, and that is 4x plus 5. I'll write it out here, I guess. That's this one here. BF, let's see here. Oh, that's the whole thing. Okay. That's 9x. And that covers the whole thing. D is a centroid. Remember, that's the point where all the medians intersect. And what do we know about medians? Where they intersect divides the median into 1/3 and 2/3. So 4x plus 5 I didn't write it in here. We have the long one here, that's BF. And then we have this section, which is 2/3. You can see that. So 4x plus 5 must be 2/3 of 9x. Well, 2/3 of 9x would be 6x, right? So we get 5 equals 2x, or x equals 2.5. Did I make any mistakes here? Not that I ever would, of course. 2/3, 6x, subtract 2x from each side, we get 2x. Well, that seems to be right. Let's check it out and see what we get here. That's 10 plus 5 is 15 here. That's 45 divided by 2. What would that be? 22 and a half. And 22 and a half minus, what was this? Oh, this whole thing is 22 and a half. What is 2/3 of 22.5? Let's check it out and make sure we didn't make a mistake here. I just went ahead and did it. Yeah, it's more obvious if you write it as 45 over 2 instead of 22.5. Now we can cancel the 2's. 3 goes into 45 15 times, so 2/3 of 22.5 is 15. It appears we got the right answer. The value of x is 5 over 2, or 2.5. That wasn't bad. You just have to recognize what it means when you say that this is the centroid. Now here's one that, I don't know, at first it kind of looks like it'll bend your brain. Let's see if it's really that bad. What is the question in this whole thing anyway? We have two triangles here, JKM and LKM. Okay, triangle here, triangle here. This third large triangle, apparently, we're not going to consider that one. Just these two. So what do we have here? Well, if KM is a median, that means it goes from the vertex to the midpoint of JL. So we could draw this in as 9 right now. We may not need it, but what the heck, we know what it is. This is a perpendicular line from the opposite side to the vertex. That is an altitude. So we know what that is. And that is also H. Now, compare the areas of the two triangles. Okay. The area of this triangle is going to be 1/2 H times 9. Now this one is an example of something I showed you way at the beginning of this video, where the altitude isn't necessarily inside the triangle. When we're considering this triangle, we have to extend the base out here and drop the perpendicular down from the vertex to the extended base. That gives us our altitude. And our base is 9. So the area, this is the area of this one. And we'll call that area sub 1, or A sub 1. A sub 2, well, that's still going to be H times the base, which is 1/2 H times 9. Well, it looked the same to me. Now, will any two areas compare regardless of the shape of the triangle? I'm not sure what they're trying to say there. It's certainly true that any two areas with the same height and base are going to have the same area. If that's what they're getting at, then Okay. But if you take any triangle and create a second triangle this way, well, I don't think it really matters what triangle it is. As long as you got the median is going to intersect at the midpoint here. So you've automatically created two congruent bases. And the height is going to be the same, so seems to me any way you drew this. You start with any triangle and go from here to here. I don't see any way that you wouldn't end up. The main thing is you have to end up with the same height or altitude and base. If you do that, then you definitely have the same area, even though they don't look much alike. That's allowed. I mean, you can consider rectangles. You can have one that looks like that, or you could have one that looks like completely different and yet have the same areas, even though they seem to have almost nothing in common except that they're both rectangles. Same thing here. Now, any time that you can split the base up into congruents, two congruent sides, and the altitude is the same, then you're going to break it up into two equal areas. And I went ahead and graphed these lines. y1, y equals 3x minus 4. We have a slope of 3, y-intercept of -4. Here we got 3/4 x plus 5. So y-intercept of 5, slope of 3/4, and the last one here, minus 3/2 minus 4. We're right along here. We want to find the centroid. It's in here somewhere. And remember, the centroid is where the medians intersect. The median is the line that goes from the midpoint to the vertex. So we're going to have to figure out what these points are. Then we're going to have to find the midpoints. Then we're going to have to find the line that connects them. And when we have equations for those lines, we'll set them equal and figure out where they intersect. It'll make a lot more sense if I actually do it. So, let's see where, let's find this point here, 3x minus 4. We'll set these two equal. Well, where should I write that equation? Yeah, put it over here. We'll have 3x minus 4 equals 3/4 x plus 5. Okay, let's subtract 3/4 x from each side and get 2 and 1/4 x. We'll add 4 to each side, equals 9. Well, that's the same as 9 over 4x equals 9, or x equals 4. Now, if x equals 4, we can put that into either one of these lines. This looks easier. And we'll get our y-coordinate. So, we got 12 minus 4, which is 8. And makes sense. So this is the point 4, 8. What about this? This point here is where this line intersects this line. Okay, I set this equation equal to this equation and did that in the same spot over here. A little rearranging, we get minus 9/4 x equals 9, or x equals minus 4, and y equals 2, which makes sense. There's minus 4 and that's 2, so our answer actually makes sense over here. So let's write minus 4, and 2. That's this point here. What about the midpoint? Well, now that we have 2 points, we can get a midpoint. Maybe I can... I'll work over here again. Remember, our midpoint is just the average. We'll take the x-average, 4 plus minus 4. Over 2. And our y-coordinate is going to be 2 plus 8 over 2. Well, this is 0. And this is 10 over 2, or 5. That puts our midpoint right there at 0, 5. Now, unfortunately, we need a line that goes from the midpoint to this point here. Well, we don't know this point yet, do we? We've got one more equation to solve. That's where we set this line equal to this line. Well, set the equation for this line equal to the equation for this line. And the point that satisfies both equations will, of course, be the intersection of the line. So we set up our equation here, and the answer probably won't surprise you. The 4's will just add 4 to each side, and they drop. Now, we can add 3/2 x to each side and get, what, 4.5 x equals 0? It really doesn't matter how many x's this turns out to add up to. We get a 0 on the other side, which means x must be 0. And if we plug that up in here, in either equation, we get that y equals minus 4. And like I said, that's probably not a big surprise to you, because this looks like the point 0 minus 4, doesn't it? But remember, we have actual points and equations for the line, so we should be exact about this. I don't think the idea here was to eyeball it. I think it was to actually find the exact intersection points by solving these equations. I could be wrong. That's the way I'm doing it. If we drew grids in here, then we could just eyeball everything. Would be possibly less precise. Now the centroid is the intersection of all the medians. Here's one median here. We found our point. Our vertex point, and then we found our midpoint. Now here's the tricky part. Let me draw this in first. If we did everything right, all we need to figure out is the distance from here to here, because 2/3 along the way will be the centroid. That's from our previous theorem, which showed that the point where all these lines intersect is at the point where, if it intersects, say, if they intersected, say, here at C, and this is A, and if this is the point, say, L, then, as we know, AC equals 2/3 of the whole thing, which is AL, in other words. So all we have to do is figure out how long this is, go 2/3 of the way. And by the way, if I didn't mention it, the long side of the median is always the side closest to the vertex. In other words, this is the 2/3 part. If I drew a median, say from this vertex to the midpoint of this line, The 2/3 part would be this from the vertex to the centroid. The short part is from the side to the centroid. The long part is from the centroid to the vertex. Otherwise, once we had the length here, we could go 2/3 from here to here or 2/3 to here. How would we know which one? Well, the long side is the side closest to the vertex. So what is it from here to here? Well, we're kind of lucky, aren't we? We just happen to choose a side to find the midpoint of and an opposite vertex, which all lie on an axis. Makes our distance formula super simple. We got 5 here and 4 here, which makes it 9. 2/3 would be 6, so we got 4 and 2, and, well, I guess the one that I guessed at is pretty much it. If we drew in the other medians, we would find that they intersected here also. But thanks to our 2/3 rule, we really don't need to. This has to be the centroid. There's no way around it. This is the midpoint. This is the vertex. 2/3 of the way down this is where the other two would intersect. So we're actually done. It's not quite as bad as it looks. So at first glance, you might think you're going to have to find all kinds of medians and to figure out the point where they intersect. In fact, I think I had said something like that earlier, where find this line and another one and figure out where they intersect. But that would be the long, slow, and not very bright way of doing it. The smarter way is to take advantage of our 2/3 rule and just find this point and we're done. Well, that's about it. Oh, and I guess I should have explicitly written that the centroid is the point 0, 2. I think that's kind of obvious from the fact that it's on the y-axis and at the point 2 here. But okay, now that really is it. Sorry.